I'm going to talk about is joint work with Professor David Perkinson of Reed College. So the title of my talk is Bigraphical Arrangements, which is the name of a certain class of hyperplane arrangements associated to a graph that Dave and I defined, and we were motivated to define and to study this class as a result of a specific conjecture of Art Duvale, Carly Clivens, and Jeremy Martin, also known as DKM, about an extension of the Fox-Stanley labeling of the shear arrangement to the case of graphical parking functions. So we already heard about the Fox-Stanley labeling of the shear arrangement this Sunday during a very nice talk of Mikhail Mazin. Let me just say that the extension, the generalization that we're looking for is very different than the one that he and his co-authors studied. Okay, so I'm going to go over the history and prehistory of this DKM conjecture. Of course, our story starts in 1986 when Jianyu Shi, in his study of the Kazhdan-Lustig cells of affine Biot group of type AN-1, defined what is now known as the shear arrangement, a collection of 2 times n choose 2 hyperplanes xi minus xj equals 0 and 1 for I less than j with both indices between 1 and n. And among other things, she proved that the number of regions of this arrangement, that is the number of connected components of the complement of this collection of hyperplanes in Euclidean space r to the n, is equal to n plus 1 to the n minus 1. So for example, here is Xi 3. Of course, it lives in 3 space, but I'm showing the essentialization in the plane. It consists of 6 hyperplanes, and you can verify that there are indeed 16 regions in this arrangement. Okay, but thanks to Cayley's formula, we know that n plus 1 to the n minus 1 also counts the number of spanning trees of the labeled complete graph kn plus 1. And so I guess sometime in the late 80s or early 90s, Richard Stanley put forward this as a problem to find an explicit bijection between the regions of the shear arrangement and spanning trees of the complete graph. And I think around 1994, Igor Plok came up with such a bijection using parking functions, which are known to be in bijection with spanning trees via several different constructions. Stanley proved that this bijection works, and now the procedure is called the Fox-Stanley labeling of the shear arrangement. So let's have a quick refresher on parking functions. We also came across these several times this week. But to me, at least, a parking function of length n is going to be a sequence a1 through an of non-negative integers such that its weakly increasing rearrangement is termwise less than the sequence 0, 1, etc. up to n minus 1. In other words, it's some sequence which is termwise less than 0, 1, etc. up to n minus 1, or some permutation of such a sequence. And the name parking functions is due to Knuth, I believe, and it comes from a certain interpretation in terms of cars who want to park on a street, but I don't have time to get into that cute description.
Should be earlier.
Sorry?
That should be earlier.
Okay, maybe it's early. At any rate, just to make sure we're all on the same page, parking functions of like 3 are here, and there's 16 of them. Okay, so what is the Fox-Stanley labeling? Well, it starts off by labeling the central region of the shear arrangement. So there's always one region that's between each of these sandwiches of parallel hyperplanes for all I less than j. In other words, xi minus xj is between 0 and 1 for all I less than j. And the Fox-Stanley labeling starts by labeling the central region with the all zeros parking function, and then it inductively labels adjacent regions in the following manner. When we cross a hyperplane of the form xi minus xj equals 0, well, that means sort of that xj got bigger at the expense of xi, so we increased the jth coordinate of our parking function label. On the other hand, when we cross a hyperplane of the form xi minus xj equals 1, then xi got bigger at the expense of xj, so we increased the ith coordinate of our parking function. Here's the Fox-Stanley labeling for Xi 3. Okay, so DKM's conjecture is about graphical parking functions. The name graphical parking functions, I believe, first appeared in a paper of Posnikov and Shapiro, but the concept goes back further because these are exactly the same as the superstable configurations in the Abelian-Sandpon model, which in turn are dual to what are called the recurrent configurations. And in the context of Riemann rock theory for graphs, these would also be called V0 reduced divisors. So let's let G be a finite, simple, meaning no multiple edges or loops, and connected graph whose vertex set is V0, V1, etc. up to Vn, where V0 has been chosen to be a special sinc vertex, and this V tilde is going to be a set of non-sinc vertices. So what is a G parking function? Well, a G parking function with respect to the choice of sinc V0 is going to be an element of the free abelian group on the non-sinc vertices, or another way to think of it is as an assignment of chips or grains of sand to the non-sync vertices, satisfying the following condition. Well, first of all, this 0 is less than equal to Ci just says that we have a non-negative assignment of chips or grains of sand. The important condition is the following. For any subset of the non-sync vertices, there's some Vi in the subset such that the number of chips it has is strictly less than its out degree in U, where by out degree in U, we mean the number of edges that Vi is incident to which are leaving the set U, that connect Vi to something outside of the set U. Another way to think of it is this condition is equivalent to saying that there's no subset of the non-sync vertices that we can fire, meaning transport one chip along each edge, leaving that set, without some vertex going into debt, going negative. So maybe this example will help clarify. We let G be this graph on 4 vertices of genus 2. Then this guy, 0, 2, 0, is a G parking function, but for example, this guy, 0, 2, 1, is not. Because if we look at this subset of V2 and V3, we can fire it and send 2 chips from V2 out along this edge and this edge, and 1 chip from along V3 out along this edge, and none of the vertices go into debt by this procedure. Okay, so now let's let G just be a finite simple graph, and the vertex set is going to be V1 through Vn. So we forget about the sync for just a moment, and with respect to this G, we're going to define what's called the, well actually DKM define what's called the Xi-G arrangement, or the G-Xi arrangement. And it consists of all the hyperplanes xi minus xj equals 0 and 1, where I is less than j, and vi and bj are an edge of our graph. So for instance, when G is this path on 3 vertices, Xi-G is this arrangement that looks like a tic-tac-toe board. And so the important thing to notice here is that because there's no edge connecting V1 and V3, we simply drop those 2 parallel hyperplanes that correspond to x1 and x3. Okay, so what is DKM's conjecture? Well, there's a very natural way that you can extend the Pax-Stanley labeling from the regular Xi arrangement to the G-Xi arrangement. You just do exactly the same thing. There's still a central region which you can assign 0 chips to all of the vertices in. And then whenever you cross a hyperplane, whichever coordinate got bigger, you increase the number of chips on the corresponding vertex. And this gives another Pax-Stanley labeling of the G-Xi arrangement. Now the first thing to notice is that we can have duplicate labels here, whereas we couldn't in the case of the regular Xi arrangement. So 0, 1, 0, and 0, 1, 0 appear as labels for both of these regions. But nevertheless, if we let G circ denote the graph obtained from G by adding this extra sync vertex V0 and connecting it by an edge to each vertex in our original graph, and we choose V0 to be the sync vertex of this G circ, so you can think of this kind of like taking a cone over a graph. Then DKM conjectured that the set of Pax-Stanley labels of this G-Xi arrangement is equal to the set of parking functions of G-circ. So this is the same as looking at the spanning trees of Kn plus 1 when we have Xi n. So that's where that extra vertex is coming from. And yes?
Now we are not counting the regions anymore.
We're not counting the regions. What we want to do is show that the set of labels obtained this way is exactly equal to the parking functions. Okay, so when you start attacking this problem, it's very natural to consider partial orientations of our graph, where a partial orientation just means we orient some, but not all of the edges in our graph. And the ones we don't orient, we call blank. So for instance, the central region consists of, the label of the central region has 2 blank edges. Here we have a blank and an oriented edge. Here we have 2 oriented edges. And the rule for labeling our regions is very simple. Okay, so each edge, Vi, Vj, determines a sandwich of parallel hyperplanes. On the one side, you orient the edge from Vi to Vj. On the other side, you orient it from Vj to Vi, and in the middle, you leave it blank. And if you do this correctly, it's a nice way to label your arrangement because you can recover the Pax-Stanley labels by simply taking the in-degree map. So you assign to each vertex the number of arrows pointing into it, and you get back the Pax-Stanley label. So now the question becomes when a partial orientation appears as a label of the Xi arrangement. And we have a somewhat clumsy way of describing when that occurs, involving potential cycles of our orientation. So a potential cycle of an orientation, of a partial orientation, is just some oriented cycle that only traverses either blank edges or oriented edges in the correct way, the way that agrees with the orientation. And given any such potential cycle, we assign a score to it, which is kind of this hideous mess, which says, okay, let's count the number of steps we make in our cycle along a blank edge of our partial orientation from a vertex of lower index to a vertex of higher index, and then subtract from it the number of steps we take along the cycle along an oriented edge of our partial orientation from a vertex of higher index to a vertex of lower index. So it's this rather complicated formula. But at any rate, the theorem is that a partial orientation is shear admissible, meaning it appears as the label of a region of our shear arrangement, exactly when every potential cycle has a positive score. And this is pretty simple to prove from the Farkas lemma, which is a basic result from linear programming about when you have a solution to a system of inequalities. One thing to note is that, of course, this forces our partial orientation to not have any directed cycles in it, because then there would certainly be one from a higher index to a lower index, and we'd have a negative score. So here's a quick example. I don't think I need to go into this into too much detail, but we have G being this cycle on 4 vertices, and this is our partial orientation. It's not shear admissible because if we take the cycle V1, V2, V3, V4 back to V1, then there's one step from a lower index vertex to a higher index vertex along a blank edge, but there's also one step from a higher index vertex to a lower index one along the oriented edge, so the score is 1 minus 1, which equals 0. And indeed, if you sum up the inequalities that you get from this partial orientation, you note that they give you a contradiction. So that's all that Farkas is on this topic, essentially. Okay, but one important observation to make about our considerations is that there's a certain family of partial orientations which is easy to see always is shear admissible, and that's the set of acyclic total orientations, because then we can never have a potential cycle, right? And it's known, I'm not sure who was the first to observe it, but you can find this in a paper of Benson, Chakrabarty, and Tatali, that acyclic total orientations are mapped by this in-degree map bijectively to the set of maximal G-circ parking functions, where maximal means with respect to the natural partial order on the free abelian group of the non-sync vertices. And I can, on the next slide, I'm going to very briefly describe sort of the inverse of this map, which uses Dar's algorithm, which is probably the fundamental tool in the theory of the abelian sandpile model. But before that, let me just remark what all of this implies for the problem. Well, it's not too hard to see that for any shear admissible partial orientation, we can extend it to an acyclic total orientation just by choosing some orientations for all the blank edges. And therefore, its in-degree sequence is going to be less than or equal to the in-degree sequence of our acyclic total orientation. On the other hand, it's also not hard to see that when C prime is a G-circ parking function and C is some configuration that's non-negative and less than or equal to C prime, then C is also a parking function. So the upshot is that the in-degree sequence of any shear admissible partial orientation has to be a G-circ parking function. The hard part of the DKM conjecture is to show that all such parking functions appear as labels of the shear arrangement. Okay, so this slide is showing one run of Dar's algorithm, and unfortunately, I don't think I really have time to go into too much detail about what's going on, but the idea is this. If we start up here with a partial orientation, or actually an acyclic total orientation, and note that now we are including the sink. We take this in-degree map, it gives us a G parking function, a maximal G parking function, in fact, which is the same thing as a superstable element in the abelian sandpile model. And there's a notion of duality between superstables and recurrence, and we dualize to get a recurrent configuration. And from there, we carry out this procedure that's known as Dar's algorithm, where we fire the sink of our vertex, and then stabilize by firing any vertex whose number of chips is greater than or equal to its degree. And as we carry out this procedure, every vertex will fire. And also, if, as we carry out this procedure, we orient the edges that we fire along, we get, as a result, a certain acyclic total orientation that happens to be the one that we started with. So that's sort of what's going on here. Okay, but one thing that Dave and I noticed right away while we were studying this problem is that the G shear arrangement is, in a certain sense, a rather unnatural object because it depends heavily on the choice of labels and indices of the graph that you're working with. So if you relabel the indices of a graph, it can change like the combinatorial type of your arrangement, but also even the number of regions, for instance. And so we wanted to kind of make the problem more symmetric by translating these hyperplanes along their normal in such a way that the resulting arrangement doesn't depend on the choice of labels. And so we defined the G semi-order arrangement to be the set of hyperplanes xi minus xj equals 1 for all vertices, for all edges in vi, vj in our graph. So for instance, this is for the graph that's the complete graph on 3 vertices. And you'll notice that it has this kind of more symmetric Star of David pattern. And there's another thing that's really nice about this G semi-order arrangement, which is that it's much easier to say when a partial orientation is semi-admissible. So a partial orientation is semi-admissible exactly when every potential cycle has more blanks in it than arrows, more blanks than oriented edges. And as a result of this simple description, we were able to extend this kind of Dar's algorithm map from maximal G-circ parking functions to acyclic total orientations to be a map from arbitrary G-circ parking functions to certain kinds of partial orientations of our graph G, such that the image of this map lies in the set of semi-admissible orientations. Every potential cycle of the output will have more blanks than arrows. And so this slide, again, is describing what's going on there. I can't say too much about it again, except the key idea is the following. So now, if we start with an arbitrary, not necessarily maximal, superstable, then we get an arbitrary recurrent, which is not necessarily minimal. And so as we're carrying out Dar's algorithm and firing these vertices, sometimes we fire a vertex and send chips or grains of sand to a neighboring vertex which was already unstable at the time that we fired. And when we do that, instead of, as before, where we would orient the edge from vi to bj, we mark that edge blank. And therefore, we get a partial orientation and not a total orientation of our graph. But again, so this is kind of reversing the integrity. Oh, I can't get too much into this. Okay, but what is the upshot of this construction? Well, it's the following. We already knew that every Pax-Stanley label of any arrangement of this sort has to be a G-circ parking function. And on the other hand, given a certain G-circ parking function, we were able to produce a semi-admissible partial orientation whose in-degree sequence is exactly that parking function. So we've shown that the set of Pax-Stanley labels of the G semi-order arrangement is exactly equal to the set of parking functions of G-circ. So therefore, by making the problem more symmetric, we were able to solve it. But what we really cared about was the G-Xi arrangement and not the G semi-order arrangement. So then Dave and I started playing around with, well, is there a way we can kind of deform the G semi-order arrangement into the G-Xi arrangement by translating all these hyperplanes along their normals? And we noticed something kind of interesting going on here, which led us to make the following conjecture. Okay, so this shows the G semi-order arrangement for G, the complete graph on 3 vertices, and this is the G-Xi arrangement. And we can get one from the other by sliding these hyperplanes down, here, and this one up. And what we noticed was that in the process of sliding, although new regions are created and destroyed, the set of labels, of Pax-Stanley labels of all our regions, always remains the same. So we can only kill regions that have duplicate labels. For instance, let's say we were moving this hyperplane here down in the direction of this arrow. Well, then we can kill this region that has 0, 0, 1 as it's labeled. But that will only make this other region bigger. And we're never able to simultaneously kill the region labeled 0, 0, 1 here and the region labeled 0, 0, 1 here, unless we squash the central region. So what we noticed was that as long as the central region is preserved, the set of Pax-Stanley labels remains the same, regardless of what these parameters are. And so that motivated us to define what we call arbitrary bigraphical arrangements. So a bigraphical arrangement is the following. For every edge, vi, vj, we choose some parameters aij and aji, and we call the list of parameters A, just the parameter list, and we guarantee that there is a central region for our arrangement by saying that there has to be some vector x in R to the n, such that xi minus xj is less than aij and vice versa. And then we define the bigraphical arrangement to be the set of hyperplanes xi minus xj equals aij for these parameters for all edges in our graph. So one thing to note is that any such bigraphical arrangement is isometric to one where all the parameters are positive. That's because we can take this vertex x that lies in our central region, we just force such a vector to exist, and we translate it to the origin, and that forces all the parameters to be positive. So you could just think in terms of positive parameters if you wanted. And so examples, of course, the G shear arrangement that we were interested in studying, the G semi-order arrangement, and some other ones that people would like to study. Okay, and similarly, we can define scores for potential cycles of orientations, and we get this exactly the same thing about A admissibility when the score, which now depends on the parameter list, is positive. Okay, and so Dave and I were able to prove this sliding conjecture, but we were able, so the theorem is that for any parameter list and any parking function, there is some admissible partial orientation whose in-degree sequence is exactly equal to that parking function. So therefore, the set of Pax-Stanley labels for any bigraphical arrangement is equal to the set of parking functions for G-circ. But the funny thing is that we don't use anything like sliding to prove this. We kind of prove it from scratch. So we give it, in fact, a different proof in the case of the G semi-order arrangement. And the proof that we do give is, it's inductive, but it's not really constructive, in the sense that we rely on this following sort of topological lemma to build up admissible orientations with prescribed in-degree sequences. So I won't get too much into this, but what it says is that under certain conditions, when we start with a partial orientation here that has some blank edges and is A admissible, well, we can take one of those blank edges and add an orientation and maintain A admissibility, but we don't have exact control over which edge is added. So we don't have a procedure for building up an A admissible orientation given some parameter list. Okay, so once we started to realize that this class is kind of an interesting class of hyperplane arrangements to study altogether, we looked at some enumerative consequences and properties. And it turns out in the case when you have generic parameters, some really nice things go on. So for instance, the characteristic polynomial of the graph becomes this specialization of the Tup polynomial. And also, therefore, by Zaslavsky's theorem, we can count the number of regions for generic parameters in terms of this kind of strange evaluation of the Tup polynomial at a non-integer value. So every math talk is supposed to include a joke. I don't think I really have time for this, but this is just a funny interpretation of when a random partial orientation is generically admissible, because you can mess around with different interpretations of the Tup polynomial. Okay. Let me just say, yeah, so I'm going to end with three further directions in increasing order of ambition. So the first is that, well, we know when the maximum number of regions of the bigraphical arrangement is achieved, that's when A is generic, and in that case, we get this nice Tup polynomial evaluation. When is the minimum number of regions achieved, and what is that minimum? So in the case of G being the complete graph, we know that the minimum is n plus 1 to the n minus 1, and it's achieved by the Xi arrangement, but what about for other graphs? So secondly, can we generalize to higher dimensions, i.e. simplicial complices? So that was originally DKM's motivation. I haven't thought too much about that. And last, is there some way to get this graphical parking function story back in the realm of representation theory or Lie theory? Obviously what she was looking at first. So maybe somehow using Kac-Moody algebras? I don't know, that's kind of like a wild dream. Anyways, thank you all for your attention. The papers are available on the archive, and the slides are available on my website.
Are there any questions?
Regarding problem number 1 on the last slide, do you think that that's going to happen when, for the G-Xi arrangement? Do you...
No, it doesn't. I know for sure that, well, first of all, it depends on the way you label your vertices, as I said.
Sure.
But here's something that Richard Stanley asked me, which I think is a nice question. Is it even the case that we can always use 0, 1 parameters to minimize the number of regions?
Do you have some examples where it's not the case?
Yeah, at least some small cases.
Would love
But
to see 'em.
I don't know for sure. Yes?
What does it mean to generalize to higher dimension?
So that would be,
Like hyperparameters?
no, it would be like if our hyperplanes were like xi minus xj minus xk, so they involved 3 variables. And somehow that would be like we had simplicial composites.
The original Stanley's proof was subjectivity. So he would reconstruct objectivity. Yeah, objectivity. So this also gives a new proof to the original
Yes, that's true.
factor
It gives
for
a
k
new-
equal 1.
Right. So it's easy to count the number of regions using like the finite field method or something for the number
Well,
of regions.
yeah. So you can look at those minimum accuracy. Yeah, number of regions is
Yes.
not that. Okay, so that's
So it's a new
that's an
proof.
independent proof
Yes,
to
that's true.
the objectivity in the region. And what about K-share arrangements?
That's a
Graphical
good
K-share
question.
arrangements?
So that would be kind of like also weighted graphs or multi-graphs. I think there needs to be some kind of genericity condition similar to the one that the central region exists. So we kind of have to guarantee that certain regions exist. But I think it should be able to
It
carry out
should be true.
It should be
for-
true.
for-
if we have multiple parallel edges.
So I think we might have to leave further. Or maybe one more, why not? You can choose.
So,
I hate it when I miss a joke.
okay, well, it just says the following. If G is planar and G star is its dual, then the probability that a random partial orientation is generically admissible is the same as this weird probability that after removing each edge from the dual graph with probability 2/3, the resulting graph is connected. And the proof goes through this polynomial interpretation. It might be possible to give kind of a direct multi-jective proof of this fact. It's not much of a joke, I know, I'm sorry. I had another one about, chickens and it just didn't pan out.